Hello everyone, February the 8th. Alright, let's play the game today. The LeetCode game. One of the most fun, sometimes frustrating game. Court number of bad pairs. Court, it's count. Jeez, man. Count number of bad pairs. Given a zero index integer array, a pair of indices is a bad pair if I smaller than j and j minus I is not equal to nums j minus nums I. Return the total number of bad pairs. So we have 4, 1, 3, and 3. 0, 1, 2, 3. So a bad pair is ij such that j minus I is not equal to nums j minus nums I. So nums j minus nums I. Okay, might be better to find the good pair. Right? It might be easier to find the good pairs. So what we're looking at, right? So let's say we start from I equal to 0. Okay. So j can be, 1, 2, 3, which means I have the range of what j can be is 1, 2. Now, yeah, I have j can be, j is 1, 2, 3, which means j minus I can be 1, 2, 3, right? And nums I is 4, right? Nums I is 4, which means nums j can be 5, 6, or 7. And all I want to know is if any of those, if nums 1 to 3 is corresponding to this. Like how many corresponding to this? This is to finding the ones that's a good pair. So a good pair must be like you know what the numbers needs to be for it to be a good pair, right? But the thing is, you have to go through them. And what we want to see is you don't have to go through them. So I have a number and the difference in the number and its value, right? So if the difference between this is going to be 4, so we find the difference between the number and its indices. So the first one is 4, second one is 0, third one is 1, fourth one is 0. Anything has the same is pairs. So basically for this case, I have one pair and the total is 1, 2, 3, 4. So it's 3 plus 2 plus 1. That's the total number of pairs. 6, so minus 1. That's it. That's how we solve it. That's exactly how we solve it. We do this, we do a count, and from the count we'll be able to say if we have size n, that's gonna be n minus 1, right? Plus 1 times n minus 1 divided by 2. So n times n minus 1 divided by 2. So this is 4. So 4 times 3 divided by 2. This is 2. So 2 times 1 divided by 2. So we have this, and then we minus every single count. Sounds good. Sounds good. Let's do this. Oh, what if it's negative? That's an interesting question. What if it's a negative? Holy crap. I think we need a map. This doesn't work. Unordered map. Actually, I'm not sure if I need to. I don't think I need to. Actually, I think this is good enough. N times n minus 1 divided by 2. Yeah, I think I can do that. I can say res nope. I can say int n is equal to p dot second, and then res minus equal to p times p minus 1. No, n times n minus 1 divided by 2. This is 2664. A good pair must have nums I all numbers that can form good pairs must have nums I minus I must have the same. All right, let's run through this, make sure that everything works, and we can submit. Yeah, looks solid. Can I do this? Oh. Okay. Not very used to this type of still not used to it. I mean, it's been a while, right? It's still not very used to this types and stuff. Alright, I'll say it's solid. I mean, it took a few tries, but it's not too bad. Yep. Exactly. Oh yeah, you can get it from here. It's pretty fast. Unordered map. Total possible pairs minus good pairs equal to bad pairs. Bad pairs plus equal to good pairs count. Diff count. Good pairs plus 1. Alright, anyway, I like the way I'm thinking. I don't like the way of this. Yeah, I'm not too big a fan. Yeah, kind of previous position. I mean, okay, it makes sense, right? The previous position, and then you have the number of pairs. Because each time you get a new one, you get a count, and then you will remove that much. Because you get a new one, you remove that much. Yeah, it makes sense, right? It makes sense, but definitely not the way that I like to do it, but it's okay. All right, let's have some time. Let's get back to this. I remember we have an error, which I'm more than happy to take a look. What's this? I might as well just go through this first, you know. We have 12, 23, minus 1, minus 30, 31, and then 5. So I have 0, 1, 2, 3, 4, 5. So we have 0, 5. Then we have 0 and 2, 3, 5, and 0, 1, 2, 2, 3, 4, 5, 5, and 0, 0, 1, 1, 3, 3, 4, 4. Okay? So after I set up the segment tree, right, when I set it up, I will update every single one with the index and the value. So first is 0, basically will come here. So we have 4, right, each one will have 4 corresponding to max subarray sum. So basically 0, this will be 12, 12, 12, 12, 12. Right? And you know what? I think it's easier to just run through in the debugger than you write here. What's the answer? Answer should be 70. Okay. All right, so we are here. Update. So, you know what? How did I get out F3? Oh, that was too fast. Yeah, that was too fast. Hold on. Try it again. Okay, tree. -23 -30 31 and 5. Okay, so tree 0, 0 is 40. Max is 40. Where'd you get 40? I think it's probably add them together as 40, right? 35. Yeah, add them together as 40. Prefix, suffix, total, everything is 40. And 0, 1, 2, 0, 2, 0, 1, 2, 3, 4, 5. So 0, 1, 2. Total sum. Max is 35. Total should be 34. Prefix, suffix is 34. That's good. And this is this. Total sum is 6. Max should be 36. Prefix 6. Suffix is that. Yeah. And then I have 35. And it's this 0, 1. That's 35. Then minus 1. And then these two. 31, 1, prefix, suffix, that's right, and then 5, then 12, 23, minus 33, 1. That's fine, perfect. I feel like it's good. And segment 0 equal to segment tree 1. I came out from here already. That was the problem. All right. That needs to be dealt with. Have to get everybody is positive. If one of them is negative, then this will be true, right? So we should say if not has negative, return sec.tree 0, 0, right? Otherwise, do this. If that was the reason why we fail, dude, that's actually a pretty stupid mistake, I shall say. Yep, I think that's a pretty stupid mistake. I just didn't realize the negative. Just go with a negative. Oh, it's still judging. That doesn't look good. That does not look good. But we pass. Look at the runtime. 14,780. That's your runtime. 14,780. 14,780 milliseconds. You know what? I'm not gonna record this because there is a better way, which is just to copy it. Okay? Which is just to copy. How do I copy? Actually, I don't know. I forgot. Python shallow copy list. List.copy. Or you do this. List slicing. So basically, we don't put them back. Do not backtrack. Okay? So we get number to index, we get a res, and we basically say segment tree. I need a copy tree. Def copy tree. Copy tree. Nope, I don't think that's the right way. I think you just get a copy outside. So we say copy shall equal to sec.tree. So we copy it. Actually, no, we should do it here. Holy crap. It can't just copy. Because it's, oh my god. Ugh. You need to do a, God Lord. Not even sure if it works. Sec.tree I. Or I can just say dot copy. Alright. Copy it. And then remove it. Get it. Backtracking, we just say sec.tree equal to copy. Int has no attribute iterator. Range. Okay, let's see if this will make it faster. So we have, oh, these are fast no matter what. Let's see if this will make it faster. Backtracking, I just do a copy. Not necessarily. Not necessarily. It could be even slower than the other one. Seriously, it's gonna be slower. Yeah. This is actually slower. So it has to be the previous version. But I feel the previous version is really, really slow already. This one's really slow already. Can't even imagine the amount of time it will take. Alright, so there gotta be something that I didn't do right. Not exactly sure what. But it's 14,780. Okay, 14,780. As bad as it can get. We don't have a tutorial, but we have solutions. Interesting. Cardane and DP. Oh, you're kidding me. It has an ON solution. Prefix sum j minus prefix this plus number of x So I need to find the number of count. Oh, you're shitting me. Suppose we're currently at index j. Let pre-x be the smallest prefix sum with the sum of all x between the end of that prefix sum and the index j minus 1. Let pre-x be the smallest prefix sum with the sum of all x between the end of that prefix sum and j minus 1. What the hell is what the hell does that mean? Maybe we should read the solution and then kind of figure it out. Okay, that just prefix sum. This is the result. Prefix sum minus low. What the hell is low? If n is smaller than 0, pre is the counter. So we'll count. What the hell is pre.count? What is this count? Are you kidding me? Unordered map. What? What is C++ unordered map count? What is this one? Oh, use count to find if n exists. N is the current number. If it exists, if it doesn't exist, if it does not exist, then pre-n equal to pre-0 plus n. If it exists, that is the minimum of pre-n and pre-0 plus n. And the low will become the minimum of low and pre-n. And then I say pre-0 is minimum of pre-0 and a prefix. And low equal to I don't understand. I don't understand shit. Alright, let's do it again. Pre-x be the smallest prefix sum with the sum of all x between the end of that prefix sum and the index. Some broken ass English right here. I don't understand what the hell they're talking about. But anyway, we want to find the maximum subarray sum while removing a number, right? So the maximum subarray sum, a subarray sum is a prefix sum minus another prefix sum and minus all the x's in between, right? Minus all the x's in between. So we need to find the smallest this, right? This is what we want to find. The smallest this. So at each j, I want to find the smallest, whatever is highlighted. And that is the smallest prefix sum plus. So that pre-x is the smallest prefix sum and with the sum of all the x's between the end of that prefix sum and, okay, now I understand what that means. Okay, so the best subarray ended at j should be prefix j minus lowest, with the lowest the smallest of all the pre. Okay, that makes sense. To update pre, we first check if array j is a negative value, since deleting a positive value would never be the possible solution. That is true. There are two items in pre affected. Pre 0. don't delete, so there are two, I think that means there are two ways, right? Array, if we don't delete, so pre-x is, if I delete x, right? Is that delete x? Pre-0 is 0, because pre-0 basically say I'm deleting 0. And if you're deleting 0, there's no effect. Right, so either you don't delete, so what you are currently at this, and you say, what if I don't delete this number? If you don't delete, this means that we have nothing deleted in the prefix sum, and therefore we could just update pre-0 if the current prefix sum is smaller. So basically at each position, you either say I will delete this value, right? If I delete this value, then that will be a this number, and you need to find the smallest that you can get by deleting this value, which means you will add up everything and the prefix sum. How do you do this without looping? And if you're not deleting this, it's just going to be pre-0, which means you don't delete anything, which is just a prefix sum, right? It's essentially just a prefix sum, because you want to find the smallest prefix sum, right? So it's just, so each one can have a prefix sum, and you just look for the smallest prefix sum. Yes. Yeah, because you have the prefix sum, so you want is the prefix sum. Smallest prefix sum, or smallest prefix sum minus some stuff. And this one doesn't minus any stuff, so it's just the smallest prefix sum among everyone. And then you have the current and minus the smallest. Okay. So if you want to delete the array j, all right, if you want to delete array j, so you either delete array j for pre-array j or delete array j for pre-0. You delete array j for pre-array j. Because I already have a pre-array j, right? So basically, I already know in the previous position of this array j, of that value, what is the smallest. Now you come to another one, right? Let's say the previous one we have deleting this. Deleting this. It looks amazing. Deleting this, because at each position, I have the smallest, which means I have the smallest pre-x, just like we are deleting these x and a prefix sum, so like this plus this is the smallest. Okay, so that is what we have. And then when you get a new one, and you have to remove it as well. So if you have to remove it, now I have the previous value, so you have to add that, right? You have to add that, but how? Follow the definition to include the current index j. I'm not so sure. Why you just add, how does that make it smaller? I could just expand. I could just expand the previous, right? Because you see this is the prefix. Because it's from I to j, right? It's from I to j. I'll read them one more time. Pre-x is the smallest prefix sum with the sum of all x between the end of that prefix sum. Smallest prefix sum with the sum of all x between the end of that prefix sum and the index. The sum of that and that. The smallest prefix sum. Okay, the smallest prefix, because I need to remove all of the x's. Right? I need to remove all the x's. And I have a smallest prefix sum plus all of the x's. And I say one more time. Pre-x be the smallest prefix sum. Okay, that prefix sum is the sum of all x between the end of that prefix sum and the index j minus 1. The best subarray ended at j should be prefix sum j minus lowest, where lowest is the smallest value in the pre. So yes, we are finding the smallest of this plus remove everything in between, right? So depending on where I is, it can change. Oh, but array j is smaller than 0. Pay attention to that. Array j is smaller than 0. So if I already have a pre-array j, which is the smallest of this thing so far, right? We have the smallest of this thing, which means we have a prefix sum up until I, and then up until I minus 1. And if I'm I minus 1 to j, I have all of, not including j, before j I have all the array j removed. So that plus that has reached the smallest. Now you have array j coming in. So for array j, which is a negative value, if you add to it, it can make it even smaller. And there's no other way it can make it small because it's already the smallest. What you have originally is the smallest. And if you say, I want to add my current one, but I want to readjust the previous one, then you're not going to get a smallest. Okay, that actually makes sense, yes. If I want to delete array j, then we just add array j because it's the smallest, it will get the smallest. That's correct. Okay, what is this? Delete array j for pre-0. Which means if I don't delete any value so far, and array j is the first one I delete, so I find the prefix we restart from the previous smallest prefix sum with no deletions. Yes, how can we make sure that there's no other array j in between? Because if there is, pre-array j should already include it and result in a smaller value in A to ignore B. So if we have an array j, because this pre-array j, this means we already delete array j, right? And if here your previous smallest prefix sum already include array j, include this negative value, right? If it already includes it, and then we don't delete anything, and then this is the first one we delete. And if we delete, then array j must be included. With no deletion. Hold on, I still don't understand. All right, I'm back. I'm this close to understand the solution. Very, very close. All right, let's do it one more time. Delete array j for pre-zero. Pre-zero is we don't delete anything. If we don't delete anything, we are keep track of just the smallest prefix sum. Right? We just keep tracking the smallest prefix sum, we don't delete. And we say we're going to delete array j. Okay, so we delete array j. Now, the problem is, if we just delete array j, how can we make sure that there's no other array j in between? Because if there is another array j before, that one has to be removed as well. Now we can make sure if there had been another array j before, right? And let's say it was involved, then I delete array j. Now, it does not matter, right? Because if the prefix sum, it includes an array j already. Yeah, it basically just means between the prefix sum and the current j, there is only one array j, right? If there is another array j in between, then we will be in a situation where pre-array j should already include it, because that will be smaller. Because if there is another array j in between, then we'll have a minimum the pre-array j will include it. Yes, because that will be smaller. That will be smaller. Holy, just this is some solution. How the fuck do you even come up with this? I mean, implementation wise, it's not that hard, because you know exactly what this is. You have a low to keep track of everything, right? And then you have a prefix. Yeah, that makes sense. And then if it's smaller than 0, you say if it exists, if it doesn't exist. Well, if it doesn't exist, is this plus this, the smallest pre, and then plus this, I don't understand. If it exists, then it's a pre-n. Basically, this means I do not delete any, right? I just, huh? What does this mean? Pre-0 is not deleting any. Pre-n is already deleting. Ah, we picked the smaller one. We picked the smaller one of the two. This is we're not deleting any. This is we're not deleting anything. I understand. This is we have never encountered n. This I understand. This is we have deleted n before, right? We have deleted before, so we have a pre-n, which is the smallest that we have. And shouldn't I just plus n? But they also do a pre-0, which means it doesn't make any sense. This does not make any sense, because if you do pre-0, this is smaller. This will always be small. Yeah, this doesn't really, I don't think you need to do this. I think you can just do I think you can just do pre-n plus equal, because I think that will always be I think that will always be smaller, which is just exactly this sentence, right? If there is, then this was always going to be smaller. Delete array j for pre-0. We restart from the previous smallest sum with no deletions. And how can we make sure there's no other array j in between? If there is one in between, if there is one in between, then this will handle it. So this basically says it has nothing in between. It's like it's the first array j to be deleted. and the other one is saying we have array already deleted before. You know what? This is right. This is wrong. Let's go back to Python. Yeah, this is correct. Man, exactly. How'd you even figure this out? What the hell? How do you even figure this out? I have no idea. This is some bull crap. Yeah, this is pretty hard to understand, but I think we got it. I think I know what it's trying to say. Yeah, this is saying there's no deletion. All right, there's no deletion, and of course it also says after the small prefix there's also no other n in between the end of this prefix and the current j. Right, that's one scenario. And this is another scenario where there was a previous deletion. So you pick the smaller of the two for the new one. Oh man. I think this one requires some marinade. We need to think about this more. This is a whole nother level. I mean, segment tree is hard, but it's hard from a different perspective. It's hard in terms of, it's just to grunt. You have to grind it out, but that's pretty much it. This is another level. Yeah, that's DP. DP is another level. Dude. Pretty darn hard, this one. I think what I'm going to do is I'm going to not look at it, and I'm going to reset this so we don't look at our previous and try to figure it out ourselves. And I think I need to kind of keep this in my head when I go to bed and then run through the whole scenario one more time. Yeah, that's exactly the problem, right? You got stuck. You read some people else's solution, and you understand it, but after a while you forget it. Dude, I'm telling you, this is the grind of doing this. Now, I was saying doing LeetCode is like playing games, and usually you don't have the grinding, but the real grind is you solve a problem, and a week later you forget about it if it's somebody else's solution. I mean, for me, there's really no. I mean, if you look at all these questions that I just put out there, I think most of them I have solved before, even on my own, or I look at other people's solution that I understood. But after a week, 2 weeks, you do forget, and I don't have any good solution for this. You just repeat, do it again, and do it again. You do it many times, and then eventually you will get it. I mean, what about like all these like segment tree, right? It's an algorithm. It's invented by somebody else. What about Dijkstra, right? What about DFS, BFS? All of these things, they're all invented by somebody else. We read it, we understand it, and then how do we know how to use it? We just keep using it. Union find, right? How do we know how to write union find? Like I ask you, whiteboard it. Write union find on the whiteboard right now. Can you do it? And if your answer is you cannot, that just means you haven't practiced enough, right? And same with the solutions, we just haven't practiced enough. And the hard part is these solutions are very specific to the problem, so it's not generalized, like this one, right? Whatever the heck this is, it's just amazing, a piece of genius. It doesn't show up in other problems. It's not like union find. It's not like segment tree, even though I really hate segment tree. But it's not like this. This at least you have a structure. So you hit another problem with segment tree, you can practice again. You do it a couple of times and you understand. But these are just very specific, very very specific. We don't get to practice this, and each like this type of complex DP problem, they have their own way of thinking. It's hard to generalize. I'll give another example. KMP. Right, KMP, to find if a string exists in a text, right? And KMP is a famous algorithm that can solve it in linear time. Again, I've done it, I don't know, 5 times maybe, but still, it's a very, very hard algorithm, very hard solution to memorize. No, I don't know. It's just, you don't memorize solutions. You try to find out the general way of thinking. That's the only way that's generalizable. Solution itself is not, unless it's a mature algorithm. But you got me, like problem like this, like how do we generalize it, right? How do we arrive at this? I mean, I think we can arrive at this step. I think this is possible if you really kind of break it down, right? What is a subarray sum? Prefix j minus prefix I minus 1, that is a subarray sum. What is a subarray sum? When you remove a number, you do this. That's the subarray sum, we remove the number. So the question is to find the minimum of this, okay? And if we have to iterate through, right? So if we iterate through j, that means for each j, we want to find the smallest of this whole chunk, right? Now the problem, we've transformed the problem into finding the smallest, some prefix sum, right? Plus the number of the value we want to delete, right? The number of value we want to delete. Okay, we can get there. So now we also know the number we want to delete must be a negative value. This we can analyze that. That means whenever we hit a negative value, then we need to decide whether we can create a smallest this thing, right? Each time we hit a negative value, we want to say if we can find a smallest this thing. So now the question is transformed into how do we find the smallest of this thing, right? How do we find it? And because of it's a DP in nature, so we have some friend. We have the previous times when we hit the same number, right? The previous time we hit the same number. So we can use that for help. We say, okay, let me look at the previous time when we hit the same number. Now we get the smallest, right? We get the smallest of this. And when we hit the current one, and if we want to delete it, right, then we should just add it to it. That I can get behind. Now, the hard part is this, right? Is this, which is the previous time. Or you can say maybe, right? Maybe if we don't delete anything, if this is the first, right? If this should be the first time when we delete it, then you should do the pre-zero thing, right? That could be the first one that we delete. Or it's not the first one that we delete. If it's not the first one we delete, we can rely on the DP. If it's the first one we delete, we cannot rely on the same DP. We'll have to find something else. Then we do that. Or we can also say we don't delete, right? We can also say we don't delete. See, this is the generalizable part of doing a DP problem, right? Because DP problem, at the end of the day, it's always brute force. DP is brute force, but brute force with a smart way to minimize the number of states you have to consider, right? If basically you find a minimum possible state that you can describe the problem. In this one, that is the minimum number of states. When you hit a negative value, there are 3 different scenarios. Number 1, you do not delete it. We just don't delete anything, right? Number 2, we delete this negative value, but we say this is the first such number we delete. Just the first one. And number 3, we have deleted this number before and we want to delete it again. That's the 3 scenarios, and those 3 scenarios created created the state, right? The state of the problem when you hit the certain number at a certain position. Yeah, this is the generalizable skill that we need to learn and apply to all DP problems. The specifics of each problem will be different. It will always be different. But this way of thinking, right? This way of thinking, because the problem saying we want to delete something, and we don't know which one we should delete. We don't know whether we should delete, right? That's why the DP, that's why the problem is difficult. And when you go DP, which you are essentially iterating through all the states, then you say, okay, I'm hitting a number that has the potential to be deleted because it's a negative. So I need to iterate through all the states. So we definitely gonna have a no delete state, and then we have a delete state. Now usually these type of problems have these two states, and that's it. You either don't delete, there's a certain way. You delete, there's another way. But in this problem, when you delete, there is a further split. Because when you delete it, it can be the first time you delete it, or the second, or not the first time you delete it. And this turns out also to be different. That, I think, is a pretty difficult, pretty tough one to spot. Yeah, that will be a pretty difficult one to spot. But overall, that is how I'm interpreting this problem. Pretty darn difficult, I should say. Very, very darn difficult. But at the end of the day, if you really can do it, there's always segment tree. Now, this is a good interview question. That's what I think. I think this is a good interview question because there is a clear, you can call it brute force. Okay, there are three ways, right? You have three ways to do this. Number one is the absolute brute force. You just delete the number. Like if I am an interviewer and I give this question to you, what I want to see is first you need to realize when you delete the number, it has to be a negative. I think that's pretty obvious, right? And then I will say, doesn't matter about the performance, just give me a solution. And you shall be able to give me the solution of brute force, which means I find the number, or the number I want to delete, I remove it, I create a new array without that number. You know what? Just turn that number into 0, right? Well, I set that number into 0, and I just run Cardane, and they give me a number, right? So you get an O(n) squared solution. Fine, which is perfectly fine, okay? And when you do that, the next one I can say, can we get it better, right? You do it, can we reduce the number of scanning? And then naturally it will lead, if you have heard of it, of course, it can lead you to the segment tree solution, which runs O(n) log n, but with a lot of overhead, right? So you get that solution out. And honestly, segment tree, I mean, during my previous interviews I did, there were segment tree problem, but I never really had to write it because interviewers know that segment tree is just a pain in the butt to get it right, and it took a long time to write. So I basically just explain, say, yeah, this problem can be solved in segment tree, and usually I'll just leave it at that. But the last one, all right, the last one is really the bar raiser, right? It's the real difference. Okay, anyway, so I'll definitely have to revisit this now with my new understanding, and I think I'll produce something different from the solution, and let's hope that the new understanding will also work. Great problem. I think this is a great problem, and it's also very easy to explain to other people, right? It's I think it also has some real life application. I can't think of it right now, but I think it could be very useful. I can see this to be useful, and it's very easy. That's the thing. Sometimes the more difficult a problem is, the easier it is to explain to people. This one you can just say, I have an array, and I want you to remove some number, like all the occurrences of a certain number. I want to remove it such that the maximum subarray sum is maximized. That's it. right? You can describe the problem in one sentence, and this is really hard, this problem. Anyway, that will be it for today. I will see you guys tomorrow. Hopefully I have time to redo this again. All right, adios.